Hi, I'm Yann Stoneman, and today we'll be doing an overview of the Kafka Streams DSL. Now, my background is mainly AWS. I've got 12 certifications in that or more, and I've worked in that field for a few years as a cloud architect. And I wanted to get deeper into Kafka and Kafka streams, especially the windowing, the different types of windowing was interesting to me, how those differ. And I thought, why not just dive into the documentation itself? This is another kind of study with me type of video. So I'm just reading out loud the documentation, and whenever I have something that confuses me, I'll look it up, I'll think out loud about it, and I know this has helped some people to listen to it. I've gotten some good feedback in the comments, so keep the comments coming because it inspires me to keep making videos like this. So here's the overview of Kafka Streams DSL, and in future videos we'll keep diving deeper. But the overview itself is quite a lot of content already for a single video. The Kafka Streams DSL domain-specific language is built on top of the Streams Processor API. It is the recommended for most users, especially beginners. Most data processing operations can be expressed in just a few lines of DSL code. Okay. So there's the stream processor API where you can, I guess, make post and get requests and so forth. And then the DSL makes it less verbose. Let's look at the overview. So in comparison to the processor API, only the DSL supports built-in abstractions for streams and tables in the form of KStream, KTable, and GlobalKTable. Having first-class support for streams and tables is crucial because, in practice, most use cases require not just either streams or database tables, but a combination of both. For example, if your use case is to create a customer 360-degree view that is updated in real time, what your application will be doing is transforming many input streams of customer-related events into an output table that contains a continuously updated 360-degree view of your customers. Declarative functional programming style with stateless transformations. Okay, so this is in contrast to the processor API. The DSL has some limitations, I guess. So, because I'm saying the word only. No, only the DSL supports. Okay, so this is something that only the DSL supports that the processor API doesn't. So the processor API does not support these built-in abstractions for streams and tables. It seems like the great thing about that is that way you can manipulate streams and tables, which act kind of like databases more because you can get the current state of the table. You can treat those with the same type of language and approach, which can be really helpful, apparently, because in many applications you'll use both. That makes sense. The other thing that domain-specific language for streams supports that the processor API doesn't support is declarative functional programming style with stateless transformations. Example, map and filter, as well as stateful transformations, such as aggregations like count and reduce, joins like left join, and windowing like session windows. Okay, so I guess I'm curious how you would do those type of transformations with the processor API, but I guess what they're saying is if you do it with the processor API, it's not going to be declarative. So you might have to do multiple things, I'm guessing, to achieve the same outcome. Whereas here, you just tell it what you want and it takes care of whatever needs to happen under the hood, is how I'm reading that. With the DSL, you can define processor topologies, that is the logical processing plan in your application. The steps to accomplish this are specify one or more input streams that are read from Kafka topics. Oh, okay. Processor topologies. Compose transformations on these streams, write the resulting output streams back to Kafka topics, or expose the processing results of your application directly to other applications through interactive queries. Example via a REST API. Okay, well, I guess what they're saying here is a processor topology, like the map of your streams. It's going to have an input a transformation and an output. And each one of those steps can have more than one. You can have more than one input, more than one transformation, and more than one output if you want. After the application is run, the defined processor topologies are continuously executed. That is, the processing plan is put into action. A step-by-step guide for writing a stream processing application using the DSL is provided below. For a complete list of available API functionality, see also this stream's API docs. All right. Yeah, I guess there are some things that the API provides that might not be included in the DSL. And so if you want to see what those might be, you can go to the streams API docs. And right now we're in the DSL API, or the DSL docs. All right. Okay, I think I will continue reading the high-level overview, then skip over like map and join and go straight to the windowing, because that's what I'm very curious about. But I want to make sure I just review the basics here to make sure I have a really solid understanding of it, especially from the perspective of this piece of documentation here. So, KStream. Only the Kafka Streams DSL has the notion of a KStream. A KStream is an abstraction of a record stream, where each data record represents a self-contained datum in the unbounded data set. Nice Latin singular. Data is datum. Okay, so yeah, a KStream is what you call a record stream in Kafka Streams. And each data record is a self-contained datum. Okay, getting the vocabulary out of the way. Using the table analogy, data records in a record stream are always interpreted as an insert. Think. Yeah, because you can't update records. Once it's in Kafka, you can't change it. You can do transformations, which go into a new KStream, but you can't modify an actual KStream, the datum in the KStream itself. Think adding more entries to an append-only ledger. Yeah, it's actually kind of similar to, kind of like blockchain in that way, because no record replaces an existing row with the same key. Examples are a credit card transaction, a page view event, or a server log entry. Right, you can't, like once the card transaction has happened, that's it. You can't go back in time and change it. Why would you? Can't rewrite history. A page view event, that happened. Server log entry, that happened. Those are all different though from the current score on a game, for example, or the current balance on a bank account. That'll be covered by KTable, but that's why insert is the only way that data records in a KStream are interpreted, because they're all append only. To illustrate, let's imagine the following two data records are being sent to the stream. Alice 1, Alice 3. Okay. If your stream processing application were to sum the values per user, it would return 4 for Alice. Why? Because the second data record would not be considered an update of the previous record. Compare this behavior of KStream to KTable below, which would return 3 for Alice. Okay, so this is a KStream, and they're saying, imagine you've got a transformation after that of sum, or even just a consumer that sums up the incoming records, and it's going to take the first one. I assume that's the first one because it's coming in like that, the arrows like that. So this one was first, and then that one. So Alice 3 came in first, then you add 1 because that came next. You don't overwrite the value for the key Alice with this one. You do whatever the application processing is doing in this case. However, with KTable, that's a bit different. You would update it. So let's read more about KTable. Only the Kafka Streams DSL has the notion of a KTable. So if you want to use a KTable, you got to use the Kafka Streams DSL. A KTable is an abstraction of a changelog stream, where each data record represents an update. Okay, so if you want to do an update in Kafka, got to use KTable. KStreams won't do it. More precisely, the value in a data record is interpreted as an update of the last value for the same record key, if any. If a corresponding key doesn't exist yet, the update will be considered an insert. Using the table analogy, a data record in a changelog stream is interpreted as an upsert, aka insert plus update, because any existing row with the same key is overwritten. Also, null values are interpreted in a special way. A record with a null value represents a delete or tombstone for the record's key. Gotcha. So tombstone is an interesting word. It's probably used in computer science, but I haven't come across it yet. And I'm kind of curious, actually. Okay. Tombstone in programming. Tombstones are a mechanism to detect dangling pointers and mitigate the problems they can cause in computer programs. Dangling pointers can appear in certain computer programming languages like C, C++, and assembly languages. A tombstone is a structure that acts as an intermediary between a pointer and its target, often heap dynamic data in memory. Okay. Yeah, and I understand that Kafka does deal with heap dynamic data in memory, so I guess that's related. The pointer, sometimes called the handle, points only at tombstones and never to its actual target. The pointer, sometimes called the handle, points only at tombstones and never to its actual target. When the data is deallocated, the tombstone is set to a null, more generally to a value that is illegal for a pointer in the given runtime environment, indicating that the variable no longer exists. This mechanism prevents the use of invalid pointers, which would otherwise access the memory area that once belonged to the now deallocated variable. Okay, I'm lost. When the data is deallocated, the tombstone is set to a null. Okay, that's what the Kafka documentation said. The value for that key that was deallocated by having an updated value of, or when you say delete for that key, it sets it to null, I guess, or any value that's illegal for a pointer in the runtime, but still needs to have a value such as null, indicating that the variable no longer exists. That way it's more explicitly telling the machine that, hey, this doesn't exist, instead of causing a dangling pointer, because I guess, the application might still be referencing it, or KTable might still be trying to reference that. This mechanism prevents the use of invalid pointers, which would otherwise access the memory area that once belonged to the now deallocated variable, although it may already contain other data, in turn leading to corruption of in-memory data. Depending on the operating system, the CPU can automatically detect such an invalid access. Depending on the operating system, the CPU can automatically detect such an invalid access, like for the null value, a null pointer dereference error. This supports in analyzing the actual reason of programming error in debugging, and it can also be used to abort the program in production use to prevent it from continuing with invalid data structures. Okay, so is it that the CPU can automatically detect if there is a tombstone, like a null? Yeah, because tombstones are a mechanism for detecting that, and the CPU can automatically detect that. Wow, so it's really low level. In more generalized terms, a tombstone can be understood as a marker for this data is no longer here. For example, in file systems, it may be efficient when deleting files to mark them as dead instead of immediately reclaiming all their data blocks. In file systems, it may be efficient when deleting files to mark them as dead instead of immediately reclaiming all their data blocks. Oh, okay. Because, yeah, I've heard of I don't know if this is related, but I've heard of garbage collection in Java. It takes actual processing power to clean up files and reallocate them and make them available. So it can be faster to just mark, dead. I guess it's kind of like when you're organizing, just to put a sticky on a whole pile of stuff and say, this needs to be donated, instead of taking care of actually bringing it to the donation location right away in that moment. Better to wait till maybe you have a few other donation files and do them all in one batch, perhaps. The downsides of using tombstones include a computational overhead and additional memory consumption. Extra processing is necessary to follow the path from the pointer to data through the tombstone. And extra memory is necessary to retain tombstones for every pointer throughout the program. Right, because if you don't clean it up right away, then there is some extra memory needed that would otherwise be cleaned. But I guess it's a trade-off, because in that moment you can also have more efficiency. You save that processing power in that moment. One other problem is that all the code that needs to work with the pointers in question needs to be implemented to use the Tombstone mechanism. One other problem is that all the code that needs to work with the pointers in question needs to be implemented to use the Tombstone mechanism. What are programming language principles and paradigms? Okay, just sounds like you need to write code to handle the pointers. No popular programming language currently uses tombstones. However, built-in support by the programming language or the compiler is not necessary to use them. Okay, so they're currently not used like with built-in support, but you can still use them. Okay, that was a long aside for this computer science concept. So just reading that again with that new understanding. Also, null values are interpreted in a special way. A record with a null value represents a delete or tombstone for the record's key. All right, so to illustrate, let's imagine the following two data records are being sent to the stream, Alice1, Alice3. If your stream processing application were to sum the values per user, it would return 3 for Alice. Why? How come 1 plus 3 is 3? Why? Because the second data record would be considered an update of the previous record. Oh, so I was wrong earlier. 3 is the second record in the way they're writing this. Alice1 comes first, then Alice3. And in this case of the KStreams, if you do a sum with a KStream on those two records, you get 4. If you do a sum on Alice with a KTable, which is a changelog stream, the first record is 1, then you get a sum of 3, because KTable can only have one value at a time for a certain key. Effects of Kafka's log compaction. Another way of thinking about KStream and KTable is as follows. If you were to store a KTable into a Kafka topic, you'd probably want to enable Kafka's log compaction feature. Example, to save storage space. Let me read that again. If you were to store a KTable into a Kafka topic, you'd probably want to enable Kafka's log compaction feature to save storage space. However, it would not be safe to enable log compaction in the case of a KStream, because as soon as log compaction would begin purging older data records of the same key, it would break the semantics of the data. To pick up the illustration example again, you would suddenly get a 3 for Alice instead of a 4, because log compaction would have removed the Alice 1. In a KStream, you would suddenly get a 3 instead of a 4. Hence, log compaction is perfectly safe for a KTable, a changelog stream, but is a mistake for a KStream, a record stream. Okay, no turning on of log compaction on a KStream. Okay, so I want to just get a little quick review of log compaction in Kafka. I probably won't read all of this right now, but I'll just read the first paragraph. Log compaction ensures that Kafka will always retain at least the last known value for each message key within the log of data for a single topic partition. It addresses use cases and scenarios. Well, actually, that first sentence is enough to explain what was just said in the other documentation. Because log compaction kind of just sounds like what a KTable is. You're just saving the last known value. That's what a KTable is. So to me, log compaction and KTable are kind of synonymous, but I'm sure there are different scenarios for using either thing, and log compaction is probably a more low-level feature, whereas KTable is a more high-level abstraction. All right, so hence log compaction is perfectly safe for a KTable, a changelog stream, but it is a mistake for a KStream, record stream. We have already seen an example of a changelog stream in the section Streams and Tables. Another example are change data capture, CDC, records in the changelog of a relational database, representing which row in a database table was inserted, updated, or deleted. KTable also provides an ability to look up current values of data records by keys. This table lookup functionality is available through join operations. See also joining in the developer guide, as well as through interactive queries. Okay, so KTable provides the ability to look up current values of data records by keys. Yeah, that seems to be like the core reason you would use it. But this table lookup functionality can also be used by joining and by using interactive queries. Okay, I guess you can join two streams and then, but I don't see how that is similar to a table lookup. I guess that's an open question that I'll keep on the back of my mind. All right, GlobalKTable. Only the Kafka Streams DSL has the notion of a global K-table. Like a K-table, a global K-table is an abstraction of a changelog stream, where each data record represents an update. A global K-table differs from a K-table in the data that they are being populated with, that is, which data from the underlying Kafka topic is being read into the respective table. Slightly simplified, imagine you have an input topic with 5 partitions. In your application, you want to read this topic into a table. Also, you want to run your application across 5 application instances for maximum parallelism. If you read the input topic into a K-table, then the local K-table instance of each application instance will be populated with data from only one partition of the topic's 5 partitions. Okay. If you read the input topic into a global K-table, then the local global K-table instance of each application instance will be populated with data from all partitions of the topic. Okay, let me digest that a little bit. So in this scenario, you've got an input topic with 5 partitions, and you've got an application with 5 application instances for maximum parallelism. And if you would use a K-table in that scenario, then each of those 5 application instances will only get data from one of the partitions of the topic's 5 partitions. So I guess that could work depending on your application, but what if you wanted each of the application instances to get data from each of the partitions, from all of the partitions of the topic? What if you want each one of the 5 application instances to get all data from all 5 partitions? Application instance 1 gets from 1, 2, 3, 4, 5 of the input topic, and application instance 2 gets data from input topic partitions 1, 2, 3, 4, 5, and so forth. Got to use a global K-table for that. Global K-table provides the ability to look up current values of data records by keys. This table lookup functionality is available through join operations. Okay. You can look up the current value of data records by keys using join operations on a global K-table. The benefit of global tables: more convenient and more efficient joins. Notably, global tables allow you to perform star joins. They support foreign key lookups. That is, you can look up data in the table not just by record key, but also by data in the record values. And they are more efficient when chaining multiple joins. Also, when joining against a global table, the input data does not need to be co-partitioned, meaning you can join data from different partitions, I guess. Can be used to broadcast information to all the running instances of your application. Right, broadcasting means send the information to all, one to many, or many to many. So with all those benefits of global K-table, why wouldn't you use it? Well, there are a couple downsides of global tables. Increased local storage consumption compared to the partitioned K-table, because downsides of global tables include increased local storage consumption compared to the partitioned K-table, because the entire topic is tracked. Okay, so more storage consumption. You gotta pay more to use global K-tables. Increased network and Kafka broker load compared to the partitioned K-table, because the entire topic is red. Okay, so more network usage, more Kafka broker load, so just more storage, network, and CPU. You just got to pay more for that stuff to have the awesome global KTable. So if you don't need it, don't use it, because you're gonna definitely pay for that. So in the next video, we'll continue with creating source streams from Kafka, and then let's look at the table of contents. Today we went over the overview of the streams DSL. Creating source streams from Kafka will be where we pick up, and then we'll go into transforming a stream, including windowing, which is what I'm really curious about, and then writing streams back to Kafka, testing a streams application, and Kafka streams DSL for Scala. So that was an overview of streams DSL. I'm Yann Stoneman. Please like and subscribe, and let me know in the comments if I made any mistakes in explaining this, but I hope this helped you. Let me know if you want any more details on any of these topics. Thanks.